In this topic, we'll look at the bit-level format and design of the ARM ISA. We've referred indirectly to the bit-level machine language in prior topics when we mentioned, for instance, that an LDR offset is limited by the number of bits reserved for it in the instruction. And in the intro topic, we looked at the layout of a simple add instruction. But now we'll go through the machine language design more thoroughly. It's not necessary to understand every instruction in it, but we'll at least cover those instructions we've used so far, except for the floating point coprocessor instructions, which we'll get to in the next topic. Now, look up and consult as we go a bit-level chart of the ISA like the one showed here in the notes. And this is from page 4-2 of the ARM instruction set materials that are pointed to in the bibliography. Or alternatively, use the image that I provided in the notes, which is quoted from a site at the University of Alaska. In lecture questions, we'll frequently ask you to look up information in the first reference or in comparable ones. The chart shows the 32-bit layout of each type of ARM instruction. And as you can see, there are a number of different configurations for different types of instructions. Data processing, or multiply, there's a single data transfer, which is the load store, and so on. Bits are numbered from right to left, with the rightmost bit being 0 and the left being 31, kind of in an odd way here, 3, 1. Some of the bits are fixed. For instance, the 0, 0 here in bits 26 and 27 in data processing are an example. For another example, we have the 1, 0, 0 here in a block data transfer, etc. But most of these form bit fields, indicating things like source or target registers, operands, or just single option flags of one bit only, like S and A and B in here. A lot is being crammed into just 32 bits. And one of the interesting points of ISADesign is the way in which we make the most out of the limited bits in an instruction. Now, let's start by looking more closely at the data processing format right here on the first row. Instructions in this category include move, add, sub, move negative, RSB and or CMP, and also 8 others that we haven't used yet. Like all the formats, it starts with a 4-bit cond field in the leftmost bits. This field specifies whether the operation is conditional on prior results. If an assembly instruction has a condition like add EQ or sub LT, the 2-letter condition is indicated by a 4-bit pattern in the cond field. One pattern, 1110 in fact, is reserved to indicate always or unconditional execution, which is the most common case. So a lot of ARM instructions begin with 1110 if they're not conditionally executed. And we've seen before that conditional operations allow the CPU to avoid pipeline disrupting branches. It is interesting that this feature is so important that every machine language instruction, down the column here, every machine language instruction can be conditional. And 4 out of every 32 bits in every instruction are reserved to indicate the condition. So, question 1. Use the references, and you may find it further down in the very document we're looking at here. Use the references to determine what 4-bit pattern would be at the start of a move EQ instruction and of an add LT instruction. By way of an answer, I'm going to shift to a different page on the document here. This is page 4-5 of that same document I referenced earlier in the lecture notes, or earlier in the transcript. And you can see there that the EQ suffix, which is when things are equal in a prior comparison, has code 0, 0, 0. And then the LT suffix way down here has code 1, 0, 0, 1, 0, 1, 1. Going back to page 4-2 here, the next 2 bits in the data processing format are fixed at 0, 0. And they mark the instruction as a data processing instruction. Every category of instruction has its own unique set of fixed bits, which distinguishes it from any other category. And we'll look much more closely at the fixed bits later on. Following the 00 bits is a single bit field labeled I. That's a I, not a 1, by the way. This bit affects how the final 12 bits for operand 2 over here, sorry, operand 2 right there, are interpreted. And we'll discuss it when we get to operand 2. The next 4 bits, labeled opcode, indicate which type of data processing instruction to perform: add, subtract, and so on. And so we get to question 2. Check the references again and find out what 4-bit opcode pattern indicates an add, which one indicates an RSB, or reverse subtraction, and then find and describe the 8 data processing instructions that we haven't seen in our example code thus far. Remember that in this and later questions, part of the intent is to get you familiar with the machine language documentation so you can look things up for yourself. So again, by way of an answer, if we get down to page 4-10 of that same document, ARM instruction set data processing describes in detail the data processing instructions and includes a complete list of all the operation codes right there. Squint hard enough and you can see that add is 0100 and RSB just above it 0011. The 8 new instructions include, for instance, ADC, which is a form of add that takes into account the carry from a prior operation and includes it in the sum. This lets you do adds on 8 or more byte integers by adding the rightmost 4-byte pair and then the next 4 bytes, including the carry from the prior add. Instruction SBC does the same for the subtraction process on the next row here. There's an EOR up here, 0001, that does an exclusive OR, a bitwise exclusive OR. And then CMP, familiar operation here, has 3 partner operations, all of which do a test on condition codes, or test an operation to set condition codes like CMP, but for example, TST does an AND, not a subtraction. TEQ does an exclusive OR. And CMN, right there, does an addition. Apparently, fine control over how testing is done to save instructions in tight loops is important. There's even the obscure BIC, B-I-C down here, and that performs a negate AND operation. All of it again in the docs. Okay, following the opcode is the S bit right here. While we typically set condition codes with a CMP, or now a test, TEQ, or CMN, any data processing instruction will set the codes if you set the S bit to 1. So we might write add S, R1, R2, R3, and the S suffix sets the S bit. And then we could do a branch on the result of the add, like BEQ label. So let's move on now to the register fields, starting with RD in bits 12 through 15. And we're going to skip the RN for the moment. By the way, some diagrams or references may refer to this as RS. It's the same register either way. So RD gives the target register as a 4-bit binary number from 0 to 15. So for instance, an add R1, R2, R3 has RD of 001, indicating register 1 is the target. The RN field has or provides the first operand register. So the same instruction we just mentioned, add R1, R2, R3, has an RN of 0010, indicating register 2. Remember that the bits for the target register actually come after those for the first operand register. Now, the second operand occupies 12 bits. We've seen a variety of possible second operands. Examples, copying from the notes here, include, for instance, just 42, a constant, or anything up to 255, R3, or any other register. A register right or left shifted by 3 or any value up to 31, and then a register right or left shifted by the value of another register. And there is something alluded to earlier. Certain constants over 255 are permitted. Strangely enough, 200, 512, or even 16,711 and 680. But interestingly not 257 or 513 or many others. We'll see why in a minute. Now, getting all of that out of 12 bits is a remarkable accomplishment, and the operand 2 bits are among the most cleverly used in the ARM design or in any instruction set architecture. They're used in two different ways, as determined by this aforementioned I bit here. Let's go over each of those two ways. If the I bit is a 1, then the operand 2 bits, these 12, indicate a register and an optional shift. The first 8 bits of that would describe the shift, and that's diagrammed down here. So we have an amount of shift, and the last 4 indicate the register. The shift bits, in turn, can represent either a constant shift, like arithmetic shift right by 12, or a shift by the value in a register, like left shift, logical shift right by the value in R3. And you can see page 4-12 in our reference documentation for details on that. This is showing you the 8 bits for the shift specification. If the last of the 8 bits is a 0, it indicates a constant shift. The first 5 bits then give a shift amount, a 0 to 31 integer value, indicating how many bits to shift. The next 2 bits give the shift type. So as you can see in the chart, a 10 for arithmetic shift right would be one example. So if you had an ASR pound 12, the 8 shift bits, a 12 for the first 5 bits, that's 0, 1, 1, 0, 0, and a 1, 0 to indicate arithmetic shift right, and a 0 to show that this is a constant shift. So putting it all together, the 12-bit operand representing, for instance, R6, comma, ASR pound 12, remember the last 4 bits of the 12 is the register number, would be 0, 1, 1, 0, 0, 1, 0, 0, that's the shift, and then 0, 1, 1, 0 to indicate R6. Now the other alternative is if the last S bit, last of the 8 shift bits, is a 1. Then we have a register determined shift, for instance ASR R4. The first 4 bits, RS, give the register containing the shift amount. The 5th bit is a fixed 0, and the next 2 give the shift type as for constant shift using the same 2-bit patterns. So, for instance, ASR R4 is 0, 1, 0, 0 for the R4, fixed 0, 1, 0 for ASR, and a 1 because it's a register determined shift. And for this entire operand R6, comma, ASR R4, we would add the 0, 1, 1, 0 for the R6 at the end, and there's the 12-bit operand 2. Okay, question 3. All of this stuff is, you can see, is documented in the references. Use the discussion we just had and the references to determine the 12-bit operand 2 patterns for the following items. R9, logical shift left, 30, there should be a pound there, sorry. And R3, ASR 47, and an FP, ROR, pound 11. And that's the frame pointer rotate right shifted by 11. Had a little time to puzzle those through. If we do the LSL 30, we're going to need 30 as the shift amount. Sorry. And then 1, 1 is a, 0, 0 is a logical left shift. a fixed 0, and there's our shift specification. And it is our 9 being shifted, so 10001. So moving on to the next one, this is a register specified shift, so we use the format to the right over here, and that would be 4 bits for the R7 register, and then a fixed 0, and then a 10 for arithmetic right shift, and then finally the register being shifted is number 3, so 0011. Oh, and sorry, I missed one bit there, the fixed bit 1. So that then is our shift specification right here. And then finally the register to be shifted, register 3. And then finally, ROR pound 11. Moving the comment out of the way here, would look like this. It is a fixed shift, so we're using the left side format there. The 11, and then the shift type for ROR is 11, and a fixed 0, and then the register being shifted is the frame pointer, which is register 11, thus RO or 1011. Now the ROR, by the way, is new. We haven't used that shift anywhere in our code. It specifies a rotating or circular shift to the right. Recall that concept from the intermediate binary lecture. And then a question related to that. If you look at the shift types, there is no left shift, no left rotating shift, that is. So why don't we have a left circular shift here? And the answer, as discussed I believe briefly as well in the binary lecture, if you want a circular shift to the left by say 8 bits, you can get the same result by circular shifting to the right by 24 bits. All circular shifts can be specified as right shifts or as left shifts. Question 5. Explain why a register and shift operand 2 cannot have a pattern of any bits where the x's are and 1 bits both here and here. Why is that not possible? And the answer is that the second 1 bit would be at the end of the shift specification and would indicate a register determined shift. But such shifts require a 0 bit in the number 7 position. So the illegality of that 12-bit pattern turns out to be important later on. Okay, stepping back a notch here, all of the preceding discussion was for the register and shift operand 1, this one. If the I bit is a 1 instead, then operand 2's 12 bits represent a constant value instead of a possibly shifted register. And the rules are completely different. The easy way to use those 12 bits would be to let them represent a constant integer from 0 to 4095, which is the max unsigned integer value in 12 bits. A more conventional or older instruction set architecture might do just that. But the ARM designers decided to stretch those 12 bits in a clever way. They realized that not all high integer values were equally likely to be needed. So they reserved just the bottom 8 bits for the integer constant. And that's these down here labeled LMM. And that gives the 0 to 255 range that we've been assuming so far. But those 8 bits are viewed as the bottom byte in a 32-bit value, with the top 24 bits being 0. And the top 4 bits of operand 2 in this case, up here, specify an amount to shift or rotate those bottom 8 bits so that they can be moved about to get various larger constants. Specifically, the top 4 bits give a value between 0 and 15. But this is doubled. It gets kind of complicated here. This is doubled to give possible shift values of 0, 2, 4, up to 30. Odd-valued shifts are not possible. And the shift is to the right, not the expected left. But it's a circular right shift. So for instance, a shift of 2 pushes the bottom 2 bits around the bend into the top 2 position. An example here, if I had this bit pattern with those in the bottom 8 bits, and I had a shift by 2, which would mean a rotate value of 1 times 2 is 2, then the entire thing shifts around. These bottom 2 bits here go into the top 2 positions, and the other 6 shift down by 2 positions. Sorry, 2 positions, and that's a rotating shift. If you want to shift left instead by, say, 4 bits, you simply specify a circular right shift of 28 bits, which is the same thing. So here are some more examples of constant operand 2 values. 1110, or 14 times 2 is 28, specifies this pattern, circular right shifted by 28, or equivalently left shifted by 4, and there it would be 4 bits up. Or here, 0101 is a 5, times 2 is 10, and that would right circular shift this pattern by 10 spots, and would end up very high in the 32 bits up here. So our next question would be, question 6, what 32-bit constants do these operand 2 constants represent? You can keep it in binary form. You'll need to translate it to numerical. So, after some thought, here's an answer for you. The first one represents a shift by 16. That's an 8 times 2 is 16. So this pattern will be shifted, rotated, right shift by 16 spots and end up in the 3rd byte right here. Next one's 12, and that represents actually a shift by 24 to the right, or equivalently a shift of 8 to the left, and the pattern ends up here. Or a shift of simply none, and the pattern stays in the bottommost byte. Okay, now go the other way. For each of the values here, 4064, 32768, 1028, construct an operand 2-bit pattern that results in that value. Or, as will be the case for one of them, explain why it's not possible to do that. Can any of them be represented in more than one way? Okay, providing an answer here. The 4064 is 254 left shifted by 4, or if you like, right shifted by 28. So we wind up with 1110, that's a 14, but times 2 is 28, and then the value for 254, which is that. For 32768, that is 1 left shifted by 15. Of course, we can't do a 15 left shift, so that could be 2 left shifted by 14, which is the same thing as 2 right shifted by 18, 32 minus 14, and that would be a 01001, that's a 9, times 2 is 18, and then a 2, and so that pattern would work. But then you could also have done an 8, for instance, left shifted by, or right shifted by 20, give the same result. In that case, 1010, 10 times 2 is 20, and 0000100 for the 8. So several patterns here would actually work. 1028 looks like it should be possible, but it's not. It is, in fact, 257 upshifted by 4. But we can't represent that because 257 is 1 and 7 zeros and a 1, and that therefore cannot fit into the bottom 8 bits. Now, fortunately, you don't have to do all this by hand when coding an assembly. You simply give the constant you want in the instruction, and the assembly determines how to represent it, or it gives an error if it cannot do so. So if you wrote add R1, R2, pound 32,768, it just works. And move R1, pound 1028 would get you an error. Okay, you now know enough to decode a data processing machine language instruction or two, so let's do question 8. I'm going to give you a hexadecimal instruction. Decode it, giving the assembly language equivalent. And there'll be several steps. First, translate the hex to binary so you can look at the bits. Then break apart the fields. If needed, look up the significance of each by reviewing the lecture or the reference docs. Then write an English description of the instruction, and then finally write the assembly for it. So with all that prologue, our first instruction to break apart will be E1874203. Okay, ready for an answer here. First, the binary translation. And then breaking that into fields with an associated field meaning under each one, remembering what we've learned from the docs and lecture. So putting that in English, that's always execute a data processing format instruction with a register shift format operand 2. Do an ORR, bitwise OR operation. Don't set the condition codes. The target will be register 4. The first operand will be register 7. Operand 2 is a constant shift of 4, and in particular a logical left shift, on register R4. And in assembly, that's OR, R4, R7, and R3 left shifted by, logical left shifted by 4. Okay, so unsurprisingly, question 9, I'm going to ask you to do it the other way. Translate this assembly language instruction from assembly to an English description, and then to a labeled fields description in bit form, finally to a full binary number, and then hex. So, in English, this is on condition less than, perform a data processing RSB with a constant operand for operand 2. The target will be R0, first operand is R1, and the operand 2 is the constant value 3360. Or we can break that down as 216 times 16, it turns out. 210, I'm sorry, times 16, which is the same thing as 210 upshifted by 4, or 210 circular right shifted by 32 minus 4, or 28. And with that information, then we should be able to break it down by fields. And the field breakdown looks like this. Let's say 1101 for the less than, still the two constant zeros for the data processing, 1 to indicate a constant op2, 011 for a reverse subtraction, don't save the codes, R1 is the operand 1, R0 is the target, and then the operand 2 is a right shift by 28, and that's a 14 times 2 is 28. And this value here is 210 in binary. So finally, putting that all together as a big binary number, we'll have the following. By nipples, or 4-bit patterns, and then translating those into hex, we get B2610ED2. In the next lecture segment, we'll look at the LDR, STR, and related formats.